Hello everybody, I hope you're doing well. Welcome back to another video in our introductory calculus playlist. So in the previous video, we have gone over various techniques to solve limits such as factoring, using the conjugate, and also taking advantage of fundamental properties of limits. So in this video, I'm going to provide you another arsenal to solve certain types of limit problems. And this arsenal goes by the name of the squeeze theorem. But to really understand how the squeeze theorem works, it's best to understand it through a diagram. So consider the picture shown below, right? You have three functions, f of x, g of x, and h of x. Now, what do you notice in this picture? Well, you notice one thing, right? You know that g of x is in between f of x and h of x. And in fact, right, to be more precise, right, or to express this more formally, we know that h of x is less than or equal to g of x less than or equal to f of x. What else do you notice? You notice that f of x, g of x, and h of x all seem to intersect at this point where the x value is c and the y value is L. Now, one thing you can say is interesting, right? Oops, sorry. You know that the limit as x approaches c of f of x equals L, and the limit as x approaches c of h of x equals L. So what can you deduce from this, right? Well, you know from the picture, obviously, like that the limit as x approaches c of g of x is going to approach L. But why would that be the case, right? And the answer is really simple, right? You know that h of x and f of x, right, are the bounds for g of x. So g of x function is sandwiched between h of x and f of x. And now because f of x and h of x are both approaching L when x approaches c, g of x can't approach any other value besides L, right, when x approaches c, because then you would be breaking this condition right here, right? So you have a little bit of a contradiction, right? So g of x has no choice but to approach L when x approaches c. Now, you might notice that I'm kind of speaking informally about why this makes sense, right? So we've deduced that the limit as x approaches c of g of x must be L, right? I'm kind of, making this argument through an intuitive standpoint and kind of being very informal here. And the reason I'm kind of being informal in this video is because for the squeeze theorem, I think it's best to take away the intuitive aspect of it. And also, the demographic is mainly targeted toward, people who are trying to refresh calculus or learn calculus. So it's, I think the real takeaway for the squeeze theorem is just, knowing intuitively what it is and being able to use it. So yeah, so this concept here that you see is called the squeeze theorem, right? Because g of x is being squeezed, quote unquote, or sandwiched between two functions, h of x and f of x. And you might also see this theorem go by another name, the sandwich theorem. All right, cool. So now that we have a basic intuition for what the squeeze theorem is, I think we can just kind of jump straight into examples. So here's a first basic example. So let's say we have this. 5 is less than or equal to f of x less than or equal to uh, x squared plus 6x minus 2. And we want to take the limit as x approaches 1 of f of x, right? So what do we notice here, right? Well, we notice here that the inequality is kind of given to us, right? So we've done most of the hard work, right? F of x is sandwiched between 5 and x squared plus 6x minus 2. So all we have to do is essentially use the squeeze theorem directly, right? So we have to check that the limit as x approaches 1 of f of x equals 5. And, oh, sorry, you have to check that the limit as x approaches 1 of 5 equals 5. And that's true, right? Because you're just having a horizontal line. So every value of x on the function y equals 5 is 5. So you'll approach 5, definitely, right? And also we have to check that the limit of as x approaches 1 of x squared plus 6x minus 2 indeed equals 5. And we can directly substitute, right? 1 squared plus 6 times 1 minus 2 equals 7 minus 2, which equals 5. So we know that this check is true, right? So now because the limit as x approaches 1 of 5 and x squared plus 6x minus 2 both approach 5, right? By the squeeze theorem, right? You have to approach 5 when x approaches 1 for f of x. So this is exercise 1. So this should be a really straightforward application of the squeeze theorem. Now you might be asking, Karthik, this problem was so easy because I literally did all the hard work was done for us in this problem. What if we weren't given this inequality? Then how would you do it? So that's where example 2 might answer that question. So let's say we want to find the limit as x approaches 0 of x squared sine 1 over x. Now, a common mistake people will do is think that, okay, so x is approaching 0. So you know x squared, right, is 0 squared, right? That's going to be 0. And then 0 times anything is 0, right? So we don't care what the value of sine of 1 over x is. And that's where you're kind of, and that's where, like, technically, spoiler alert, you're kind of right, but it's not as satisfying, right? And it's kind of through the wrong explanation, right? So let's think about it this way. Well, we know that the theme of today's video is about the squeeze theorem, so let's try using the squeeze theorem. So the one big thing we have to do in this problem is figure out how to bound x squared sine of 1 over x, right, in the easiest way possible. And one thing you might want to take a note of is the property of the sine function, right? We know that the sine function is between -1 and 1, right? So when you're taking the sine of a number, right, the minimum value possible is -1 and the maximum possible value is +1, right? So it doesn't matter what expression really goes in this x. You're taking the sign of a quantity at the end of the day, right? So this 1 over x kind of really doesn't mean much for the purposes of the squeeze theorem, right? Because you're taking the sign of a quantity, right? So with that being said, right, because we know that the sine function is bounded between -1 and 1, we know that x squared sine 1 over x is really bounded between the functions -x squared and +x squared. So we know that this is true. And what we've done is we've bounded x squared sine 1 over x in terms of two different functions, right? And what we're doing here, right, we took advantage of the property of sine, right, to come up with this bounding in the most straightforward way possible, right, without making it hard on our lives, right? So what do we have to do now? We have to check that the limit we have to identify the limit as x approaches 0 of -x squared. That's going to be 0. And we have to check that the limit as x approaches 0 of x squared, right, that also equals 0. So now because these two limits, right, approach the same thing by the squeeze theorem, the limit as x approaches 0 of x squared sine 1 over x must also be 0. So these two examples provide a brief intuition about, what the squeeze theorem is and how to apply it, at least for the purposes of, you know, this playlist. So thank you very much for watching this video and looking forward to see you in the next one. Please like and subscribe and leave any comments if you have any questions.